Welcome students, welcome to the next session of Strength of Materials 1. So in the previous class we have started the generation of shear force and bending moment diagrams for the simply supported beams as well as for the cantilever beams. And then we have used so many types of loads. There we have observed point loads, UDS, uniformly varying loads, and also combination of all these loads. Now we are going for the next concept, which is having overhanging type beams. So firstly, before entering into the overhanging beam, as we have already taken an example, a overhanging beam having one side overhang and carrying UDL over entire length. Today we are going into another numerical which is having a overhanging beam. Firstly, we are going into our regular basic sign conventions for the shear force and bending moment. Please, in every class I am repeatedly saying these sign conventions because the sign conventions itself may have the question like explain about the sign conventions and important points for the shear force and bending moment diagram. That is repeatedly given in every previous paper of your R67 or the regulations of your previous batch. Okay. So please remember the sign conventions for the shear force. When we observe any section line, on the left side of the section, when there is the force going upwards, that will be considered positive. On the right side, when the force coming downwards, it will be considered as a positive shear force. Similarly, in the negative condition of the shear force, when the left side we observe downward force, on the right side when we observe upward force, thus two combination or any force having this type of condition with respect to the section, that can be considered as the negative shear force. When in case of the bending moment, when we observe any section line, on the left side when we observe this type of movement, or on the right side of the section when we observe this type of movement. So completely this condition can be considered as the sagging type movement or the positive bending moment, and in ulta case or the reverse condition we can observe the convexity in the top, and the corresponding condition can be called as a hogging moment, and it can be indicated as the negative bending moment. Okay, now I am going into the condition of overhanging beam. Firstly, only these two definitions, because these two definitions may also come in short answers also. Okay, so the condition of the overhanging beam, nothing but if an end of the portion or if the end portion of a beam is extended beyond the support. Okay, if the end portion is extended beyond the support of a beam, such type of beam can be called as an overhanging beam. So here we can observe a simply supported beam and one side is extended with a overhanging portion, and on the left side also you can observe the overhanging. Just if it is having only one side extension also, it can be called as overhanging. If it is having two sides also as extension, only this portion is there, two sides also extension, yes, that is also an overhanging beam. But a minimum of one side is overhanging there, then it can be called as the overhanging type beams. Okay. Now the point of counterflexure. There we have observed in the shear force and bending moment diagrams, the main points are at the simply supported ends, the bending moments will be equal to 0, and at the free end of the cantilever, the bending moment will be equal to 0. And also in simply supported beams, at the supports, the reaction value is equal to shear force at the supports. And also there we have mentioned shear force is changing its sign when a span. At that point, you can observe maximum bending moment. So when any span is having changing its shear force from positive to negative or negative to positive, that the corresponding span may have a point with a zero shear force. That zero shear force point will cause maximum bending moment. And in the next case, when we observe the bending moment is changing its sign or the bending moment is becoming zero, that point can be indicated as point of counterflexure. So this point of counterflexure means the bending moment is 0 or changing its sign from positive to negative or negative to positive. The corresponding point can be called as point of counterflexion. And when they are asking to give the position of zero shear force, or when they are asking to give the position of the point of counterflexure, we need to give the position with respect to any of the support. Okay, with respect to support A, the point of counterflexure is at certain distance. With respect to support A, the shear force is equal to 0 point is at some distance. Like that we should have to mention. The statement is compulsory for giving the position, because we will get X answer. They don't remember only where, from where the X is being measured, from A X is being measured. Like that we should have to give. Okay, that is the condition for the point of counterflexure. Now in today's case we are going into another type of overhanging beam which is being subjected to some point loads. In the last class we have done a overhanging beam with one side and extended, and it is longitudinal over entire length. There we have observed shear force diagram and generated the bending moment diagram also. Okay. Now I am going into today's problem. A beam of length 12 meters, simply supported beam. Okay. So a beam of 12 meters and it is simply supported beam with supports at 8 meter apart. They will not give the loading figure. Loading figure you should have to generate. Okay. So understanding the problem, you should have to generate what may be the loading figure is. Okay, the loading figure generation itself will have marks. So, a beam of length 12 meters and is being simply supported with the two supports which are 8 meter apart with an overhanging of 2 meters on each side. So, with an overhanging of 2 meters on each side, a simply supported beam is having two supports with 8 meter apart. Don't think the length of the beam is 12 meters, simply supported and 8 meter because it is the overhanging beam. That's why the beam length is 12 meters but the supports are at 8 meter apart only. On the left, on the right, I am having 2 meter overhanging portion. Right? Now, as shown in the figure, and if they mention or not, they should have to generate like this. And also, for the loading case, they have given like this. Otherwise, they will mention on the right end of the beam, there is a point load of 1000 newtons on the complete right end, and on the complete left end, there is another point load of 1000 newtons. So, in this way, they can give in the form of statement, or in this way, they can give in the form of loading figure. We can't expect whether they will give the loading figure or not. From the theory itself, we should have to generate the loading figure, how it will be. Okay, so 2 meter overhanging portion, then it is having the load application at free end and the complete right end and in the complete left end of this overhanging beam. Okay, so there are the values 1000 newtons. Now we should have to generate shear force and bending moment diagram. Firstly, what we need to observe for the overhanging beam, as the overhanging beam's analysis of the shear force and bending moment diagram will be followed according to the simply supported beam like. So, first step in simply supported beam is calculation of the support reactions. Here also in case of overhanging beam, I will calculate the support reaction at A and support reaction at B. So, the first step involving here is the calculation of the support reactions. So, what we are doing? So, first thing is vertical equilibrium condition, which is equal to sigma B is equal to 0. Summation of all the vertically upward forces is equal to summation of all the vertically downward forces. So, RA plus RB is equal to, what are the total downward loads acting? Only we are observing up and down. Where the position is on the left, on the right, whatever it is, we don't want. Only how many arrows in up, how many loads in down. So, upward, RA and RB were there. And in the downward direction, I am observing 2 point loads of 1000 Newton each. So, the total downward load is 1000 plus 1000 Newtons. So, in this way, we are getting the total downward load and RA plus RB is equal to total of 2000 Newtons. Now, for calculating any of the support, what we need to do? Support reaction, we need to calculate moment about any support. Moment about any support, that is equal to 0. So, sigma MA is equal to 0. As I am having the beam like this, these are 8 meter, 2 meter, 2 meter, and this one is 1000 newtons and this one is 1000 newtons. Okay. And here are the supports A and B. These are the support corners C and D. Now, I am calculating moment about A. So, summation of all the moments about A. So, sum of all the clockwise moment forces into the perpendicular distance 10. Sum of all the clockwise moments. I am having 1000 newtons in the clockwise direction at a distance of 10 meters from A. And is equal to, sum of all the clockwise moments is equal to summation of all the anti-clockwise moments. In the anti-clockwise direction, I am observing RB, RB, and that is at a distance of 8 meters from A. And also, not only these two, on the structure, I am having one more force. Where it is? This 1000 newtons. And about this A point, how it is rotating? About this A point, it is rotating in the anti-clockwise direction. See here, how the direction is going? It is going in the anti-clockwise direction, right? So, how our watch goes? That is clockwise. How in the reverse condition? Anti-clockwise. So, clockwise, anti-clockwise. Okay. So, here, about this point, this is giving the anti-clockwise direction. As the anti-clockwise force is RB, so in that way only it is adding. So, RB plus 1000 into, how much is the distance from this 1000 Newton point load and support A? That is 2 meters. So, 1000 into 2 meters. In this way, we have got RB answer as 1000 newtons, and then RA answer as 2000 minus 1000, which is equal to 1000 newtons. So, simply you can say as about the center line, when the length of the beam is how much? About the center line of the beam, the left hand side forces were symmetrical to the right hand side forces. See here, downward 1000, downward 1000, upward RA, upward RB with the same distance, because I am at the center line. When at the center line, the left side segment is symmetrical with the right side segment, RA and RB will be equal and will be equal to half of the total load. So, RA is equal to, RB is equal to total of 2000 divided by 2. So, that is equal to 1000 newtons and 1000 newtons. In this way, we have calculated the support reactions only. Now, we are going into the calculation of the shear force and bending moments for each span. Okay. Firstly, considering the shear force diagram. As we have already mentioned, we need to take a section from the left side, and considering the load variation, we are going with different spans. Okay. Once I have calculated RA value and we have calculated RB value. Okay. So, once we have calculated this RA and RB, no need of thinking about this RA. Only a load of 1000 is there. Only another load of 1000 is there at the position. Okay. So, our imagination should be like that. A downward load of 1000 Newton, and at A an upward force of 1000 Newton, and then at B another upward force of 1000 Newton, and then at D a downward load of 1000 Newton. So, this is the loading condition. Now, firstly I need to consider a section in between left support and the next point where the load is varying. Firstly, I am considering a section line from the left point, not from the support, from the left point. Okay. From C, I am measuring the distance of the section line. Now, from C, at a distance x, in between C and A. Why in between C and A? Because once I cross this A point, I am adding a 1000 Newton load. So, in between C and A, I am taking a section line, and which is being located at a distance x. So, after this A point, I am having another load application of 1000 newtons, because once RA and RB were calculated, we are not at all thinking they are reactions. Only there is a force. That's it. So, a force value of 1000 newtons is there at the point. So, in between these two, we need to consider the section, because once we cross this point A, there will be application of two forces. Once we cross the point B, there will be application of three forces. So, like that we are separating the spans. Firstly, in between C and A, and considering the section line at a distance x from C. So, here we are completing that condition. And on the left side of the segment, what are the forces involved? So, considering the section line on the left side, when I observe, I am observing 1000 Newton load only at a distance of x in between this C and A. So, in between CA at a distance x, so we are observing 1000 Newton downward force. So, corresponding Fx is equal to left side downwards. The corresponding force is about the section line, left side up, right side down will be positive. This left side up, right side down is positive. But here, left side down is coming, so negative shear force. Left side downward force, negative shear force, so negative of. How much is the force value? As it is 1000 newtons. So, only force I am writing. In case of movement, we will multiply force into perpendicular distance. Okay, minus 1000 newtons. And then, this is the equation of Fx for the span C to A. So in between C and A, this is the answer. Now at x is equal to 0. X is equal to 0 means as I am measuring from C, so x is equal to 0 is indicating C. So at C, x is equal to 0, which is indicating Fc is equal to minus 1000 newtons. And when x is equal to 2 meters, which is indicating at A location, and the corresponding Fa is equal to minus 1000 newtons. In this way, we have got the shear force at C and shear force at A. Now, we are going into the calculation of the shear force in the next span. Now, at some random point, again from C, and we are considering the corresponding section line. So, now this is section line in between A and B, and it is measured from C and which is being located at a distance of x. So, we are considering a section at a distance x from C, which is in between A and B. Now, what are the forces involved on the left side? Left side downward one force and also left side upward one more force, and this is the section line. As C is this point only, so this is the perpendicular distance x. As it is 2 meters, this remaining leftover distance will be x minus 2 meters. Now, these perpendicular distances are not at all needed because we are going with the point loads. Maybe in case of bending moment, this is needed. Okay. Now, about this section line, on the left side downward 1000 is there, and in the upward 1000 is there. So left side downward minus 1000 and left side upward plus Ra is there. So which is equal to minus 1000 plus 1000, which is equal to 0 newtons. So in between A and B, at any point the shear force is equal to 0. So if you want to substitute x at x is equal to 2 meters and x is equal to 10 meters, because that x is measured from sea level. X is measured from sea level. So x is measured from sea, x is measured from sea. So it is 2 meters. That for B it is 10 meters. Okay. So in this way 2 and 10 I have got Fa is equal to 0 and Fb is equal to 0 newtons. Now we are going into the next section line, where the section line is being located in the last span after B point. Why I am taking that span? Because once I am crossing one point, the load is varying. Up to B, it is involving two forces only. Once we cross the B, then we should have to involve RB. Okay. Now, I am considering the next section line at a distance of x, again from C. Now, the next section line between B and D and measured x from C. Now, it is involving the forces left side downward 1000 and it is involving an upward Ra and it is involving an upward Rb. So left side downward minus 1000 and left side upward Ra value, that is 1000, and also left side upward value, that is one more 1000. Cancelling these two, finally I have got positive 1000 newtons. So this is the shear force in between the points B and D. Now at x is equal to 10 meters and x is equal to 12 meters. So which is indicating point B and which is indicating point D, that is equal to Fb is equal to 1000 newtons and also Fd is also equal to 1000 newtons. So in this way, at C and A, at A and B, at B and D, we have generated shearing force values. Now we are going into generate the shear force diagram. Firstly, indicating the original loading structure for the reference and indicating the external point loads also. Okay, this one 1000 Ra, Rb, one more 1000, 2 meters, a distance of 8 meters, another distance of 2 meters. Now, giving the projection lines for generating the shear force diagram. And firstly, as this is the corner C and this is the corner D, A and B. Now, in between C and A, what is the shear force values we have got? We will go into the span and check the answers and we will plot here. First span between C and A, we have got Fc is equal to minus 1000, Fa is also equal to minus 1000. So, minus shear force will be indicated below the baseline. So, Fc is minus 1000 below the baseline and FA is minus 1000 below the baseline. As these two are constant values, a simple horizontal line. Okay, so minus 1000 to minus 1000, that is up to C to A. Now in between A to B. Now in the next section, at A it is 0, at B it is 0. Now I need to indicate those zeros. So at A from the baseline it is 0, at B from the baseline it is 0. Nothing. Only for your reference I have given the dots. No need of indicating the dot also. Only the simple straight line, as this span is not at all having any shear force. Okay. Now in the next span BD, as in the BD span at B we have got positive 1000, at D we have got positive 1000. Now connecting these two, at B we have got a positive 1000, at D we have got positive 1000. Now connecting these two answers, we have got a horizontal straight line value. So the constant of 1000 newtons is there in the positive, a constant of 1000 newtons is there in the negative manner. So the completion of the shear force diagram was over. So negative 1000 to positive 1000. This is the complete variation of the shearing force for this type of overhanging beam. Now we are going into generate the bending moment diagram. Okay. So for generating bending moment diagram, already in case of shear force diagram, we have got 3 spans. Again, those 3 spans only will help us. Okay. So the first span we are considering at a distance of, this is the overall indication of the shear force diagram as we have already drawn with our hand. So simple indication for the picture, negative 1000 shear force diagram and the positive 1000 of shear force diagram. So the complete loading to shear force diagram picture. Okay. Now in the bending moment diagram, firstly I am considering the first section which is located in between C to A and which is measured at a distance from C. The distance is X and it is involved like this. Now what we need to do? We need to calculate bending moment at the section. So that I am considering the section up to this level and it is having only one force of 1000 newtons and which is being located at a distance of X. So from C up to A, whatever is the section line we consider, at that section line I am involving this force only. So the corresponding mx is equal to, see here what is the mx? Force into perpendicular distance about the section line. So force into perpendicular distance which is 1000 times x. So 1000x. As it is giving this hogging type moment, I should have to indicate negative. So mx is equal to minus 1000 times the x. As this mx is the answer for C to A. In between C up to A, at any section when we want to calculate the bending moment, this is the answer. From C up to A, any point when we want to calculate the bending moment, this is the equation. There in the x, I should have to substitute the value where the point is being located from C. From C, how much distant it is. Okay. Now, the equation I am using and calculating MC and MA. As x is equal to 0, that can be indicated as C point and that is equal to 0 minus 1000 into 0 answer, that was 0 only. And the next thing, at A point, this equation is valid up to C to A only. So at A point, that is x is equal to 2 meters. Substituting in the above equation, we have got minus 2000 Newton meter, as minus 1000 into 2 meter is the perpendicular distance, force into perpendicular distance. In this way, we have got MC and MA. And then we are going into the next section which is being located in between A and B. Now I am considering the next section being located in between A and B. Again it is measured from C. So generating the free body diagram for the section, and it is involving 1000 Newton load and it is having RA, and this is at a distance of X and which is at 2 meter, and the remaining leftover distance here is X minus 2. Whatever is the X value up to B, the corresponding X minus 2 is the remaining gap, because this is the 2 meter length. Okay. Now bending moment about this section line, Mx is equal to, what are the forces involved here? It is involving a 1000 Newton force and it is involving it is involving RA also. So these two forces will produce corresponding moment. So force into perpendicular distance, force into perpendicular distance. Now 1000 into x, as this is 1000 into x is the perpendicular distance, as it is causing hogging type movement. And then the next force is RA, and the RA is at how much distance? X minus 2 perpendicular distance. And in this perpendicular distance, it is causing sagging type movement. See here how the force is going sagging way. Okay, minus 1000x plus RA into x minus 2. As we already know RA is equal to 1000 newtons, we can write minus 1000x plus 1000 into x minus 2. So with the multiplication minus 1000x plus 1000 into x minus 2, we have got mx is equal to like this, and minus 1000x plus 1000x and minus 2000. So this is the overall multiplication, and cancellation I have got mx for the span A to B is equal to minus 2000 Newton meter. Mx is equal to minus 2000 Newton meter. Force into perpendicular distance. Force is in newtons and length we are measuring in meters. 2 meters, 5 meters, 8 meters like that. Okay. So force into perpendicular distance Newton meter. Just a capital N nearby small n. Okay. Nm. Now this is for the equation for the span up to A to B. At A and at B, what are the answers? At A, which is nothing but x is equal to 2 from C, measured from C. And at B is 10 meters from C. Okay. And MA is equal to MB is equal to. It is a constant value. There is no substitution of x in this. So minus 2000 Newton meter, minus 2000 Newton meter. Now we are going for the next span, which is being located in between B and D. And the section line is again measured from the reference as C point only. Okay, so the next section line I am taking. Now, what are the forces I need to involve? Again, I am taking the reference section line, and it is involving RB, it is involving RA, and it is involving the corresponding 1000 newtons up to the section line. And this one is at a distance of x, and which is 2 meters, and which is 8 meters, and this remaining measurement is total of x minus 10. This is x minus 10. In this way, the remaining perpendicular distance between RB and the section line has calculated. With the known values, the unknown length is measured. Okay? And the corresponding mx, shall we write the mx answer? Now, mx is equal to the force of 1000, and which is at a perpendicular distance of x, and it is causing hogging type movement. And a force of RA, which is at a distance of RA. See here how much it is distant, as it is x, and this remaining distance, this is 2 meters, and this remaining distance is x minus 2. Or you can write like this, or you can use this x minus 10 plus 8 up to RA. How much is the distance? This is the distance. So x minus 10 plus 8 is the total length, that is x minus 2 only. So RA is at x minus 2, and it is giving sagging type moment. And then we are having the next force, that is RB, and which is at a distance, RB is at a distance of x minus 10, we have already calculated. So that is x minus 10, and it is causing positive type moment. See here, with respect to the section line, how it is rotating. With respect to the section line, how it is rotating. Okay, that is the clockwise or anti-clockwise or sagging type or hogging type moment. Okay, in this way I have generated the condition. Is equal to minus 1000x plus 1000x minus 2000 plus 1000x minus 10,000. Okay, so this is the final calculation we have got. Now minus 1000x plus 1000x, and as usually plus 1000x and minus 12,000x we have got. Okay. With this analysis, finally what we have got the term plus 1000x. So this was cancelled, this was cancelled. The remaining left over is plus 1000x and minus 12,000. Plus 1000x minus 12,000. Okay, so this is the equation of mx we have got finally. Now this equation is valid in between B point and D point. So at B, which is at a distance of 10 meters from C location. From C location, B is at 10 meters. So at x is equal to 10 meters, the corresponding MB is equal to 1000 times 10, which is a plus value, and minus of 12,000. As it is 10,000 minus 12,000, I can say, which is minus 2,000 Newton meter. So this is the minus 2,000 Newton meter is the answer for bending moment at B. Now in the next position where x is equal to 12 meters, that is the indication for point D. From C, 2 meters, 8 meters and 2 meters. So at 12 meters, that is the point D reference, there I have got the bending moment. Observe here. Sorry, this is wrong. We will get 0. As 1000 into 12 minus 12,000. So which we have got MD is equal to 0, as capital M suffix D is the 0 bending moment at the complete right end of the overhanging beam. So minus 2000 to 0. And in the previous step we have calculated at C, at A, again at A, at B, again at B and at D. So in this way we have individually calculated all the bending moments. Now I am generating the overall bending moment diagram. So generation of the bending moment diagram. Further, only for a simple reference, again I am keeping the loading structure. As we already know, 1000 RA, RB, and the value of 1000, C point, A point, B point, and D point, 2 meter, 8 meter, and 2 meter. Again, our bending moment diagram started with the baseline, which as it is equal to the length of the original beam, and with the loadings, I am projecting the corresponding projection lines. Now, these projection lines will help us to give the corresponding point location to calculate the bending moments. Okay. Now, I am going for the bending moment at each span. The first span between C to A. At C, I have got 0, and at A, I have got minus 2000 Newton meter. And connecting these two answers, what is the equation? Minus 1000x, single degree straight line. So MC and MB, connecting these two, I am taking the equation also. Bending moment at C is 0, and bending moment at A I have got minus 2000, and connecting these two is a single degree straight line equation. And then between B and A, or A and B, which we have got the final equation as a single answer of minus 2000. Mx for AB span is minus 2000. It is not at all having any x value. At A, at B, minus 2000, minus 2000. Now I am using that minus 2000 only. And at A already I have got minus 2000, and at B another 2000. And connecting these two, a normal horizontal line. Now the next span in between B to D. In between B to D, we have got bending moment at B is equal to minus 2000, and bending moment at D we have got as the 0 value, and the corresponding bending moment equation is 1000x minus 12,000. So single degree straight line equation. From minus 2000 to 0 value, this line equation is involved. Again, minus 2000 already it is there, and to the 0, and connecting straight line equation. As this complete structure of the bending moment diagram was completed, negative bending moment diagram, and it is the bending moment diagram indication. So in this way we are completing our BMD, and overall picture when you observe the original loading figure, and from the projection lines we have started shear force diagram, and then projection we have got the bending moment diagram from 0 to 2000, and then the constant bending moment is maintained and it is becoming 0 at the complete right end. So in this way we are completing shear force and bending moment diagrams for the overhanging beams. In the next class we are going into the next concept. Thank you.